All right, pre-calc. This is part 2 of logarithmic properties and solving equations with logs. So when you see number 3, we have to think through some of the strategies that could help us sort of like unravel this mystery that's a log. So we could use change of base formula to basically find the decimal version of everything and then perhaps make our way through it. But there's actually a more elegant solution to doing this. And that is, that's taking logs and building them together. So here are kind of the list of the properties we've got. Let's say we have logs of the same base. So let's say that the base is b, and one of them is, let's just call it x, and we're adding the same log base, but it's a different number there, y. There's actually a property that says if you are adding two logs together with the same base, then you can combine the logs with that same base, and instead of adding the two together, it becomes multiplication. You can try it with a few just random examples. Here, try it with this. Try log base 10 on your calculator of 7 plus log base 10 of 5. All right, so log base 10 of 7 plus log base 10 of 5, it gives me this decimal. All right, using the property I just unraveled for you, this would be log base 10 now of 7 times 5, 35. What's log base 10 of 35? It's the same thing. Okay, so what we do is if we find ourselves in a situation like number 3, where it's like, okay, I've got log base 2 twice on the left-hand side of the equation I'm trying to solve it, let's compress it to one logarithm, and then you are going to multiply the contents inside. So 4x times 5. All right, so this is now log base 2 of 20x, and that equals log base 2 of 40. Great. Now, what's the move we talked about last week that would undo the operation that a log is performing on something? Well, all we got to do is apply the inverse operation to log base 2. Apply inverse operation to log base 2. And hopefully, if you guys remembered anything from last week, or the previous weeks, you realize 2 to the x power is opposite log base 2. They're inverses when you graph them. So if I apply 2 now as the base of an exponential on both sides, these now cancel each other out. And you're left solving the equation 20x equals 40. Which is pretty simple. You just divide both sides by 20 and you got x equals 2. And that ends up being the final answer. So keep in mind that this property, you need to have it handy. If the bases are the same, you can combine each element of the log through multiplication. Let's check out number 4 now. Number 4 applies a log property that we used up top. If I've got a coefficient in front of a log, I can rewrite the log where that coefficient becomes an exponent. So log base, you know what? I kind of want to keep track of these. Let's do this. Let's get a list going. over here. So we got log base b of x plus log base b of y equals log base b of xy. Is it going to... Come on now. Let's go backward. Yes. Right. Come on now. Okay. Log base b of xy. Our next move is, if you've got some constant, I'll just call it a c. So c of log base b of, it could be anything, x. This is now, the c is up top. It's log base b of x to the c power. This c is now up here. Right, so this becomes super helpful because right now I cannot apply a 3 to both sides. The 3 is being blocked by the multiplication of 2 times this log. This 3 is not going to eliminate the log right there. By the way, do you guys recognize that when I write these 3's down here, I'm saying this is now an exponential function where 3 is the base and the logs become the exponents. I'm not just writing those 3's kind of randomly in there. They mean something. At any rate, you can't apply this until you have a clean log on the left and a clean log on the right. This is what a clean log looks like. Log base 3 of x squared. That's a clean log. It's 1. There's one of them, and there's nothing in front. Here, it is what it is. I could apply a change of base formula to it, but I've got log base 3 on the left. I got log base 3 on the right. No need to do a change of base. By applying now, 3 now is the exponential base. It cancels out the log property, and you're left with x squared is equal to 32. Oh, okay. So this is going to leave us with another interesting little tidbit off to the side here. So when you solve an equation like this, square rooting both sides or taking an even root from both sides always creates 2 solutions, right? X is equal to plus or minus root 32. It's just the nature of things, right? If you got x squared and you're saying where does it equal 32? I'm looking at the part before I square rooted both sides. It's going to equal 32 at 2 different spots. Well, here's the thing. Logarithms, when you use one of these properties, you fundamentally change what the log is. Remember, logs look like this graphically. They don't have any negative solutions. So when you think about this, it's like, okay, normally you'd have a plus or minus solution here. But now it's like, hey, I got to take the log base 3 of an x value. That x value cannot be negative root 32. So your only solution here is going to be the positive root 32. That actually comes out to be 4 root 2. Okay. If you were just watching the video, make sure you listen to that last explanation because you're going to have to check a lot of these. There's a lot of extraneous solutions. Oh, no, they're back. So the negative is an extraneous solution here. And it's not always just negatives. It's whatever makes the log negative. All right, we're having fun. Let's look at a couple more examples. What happens if there's subtraction between? We know addition. We know what happens if there's a constant out front. But subtraction is another story altogether. So property number 3. What happens if I change this to subtraction? Addition created multiplication, subtraction, what do you guys think it's going to create? That's right, division. It's going to be x divided by y. Okay, so addition of two logs of the same base, multiply the contents. It's now one log, that same base. Subtraction between two logs with the same base, divide the contents, and you've got one log now. So if we look at number 5, okay, number 5, oh man, we got to get this in the same window here. Back it up, there we go. This subtraction right here, not that subtraction, this subtraction right here, will create these contents now get divided, but you're still left with the log, okay? Don't start skipping steps on me. The right-hand side is 2. It is what it is. Now, you guys know what to do next. We have to apply a 6 exponential to both sides in order to break this free of the log. Now, on this other side, there's no log. We literally have to do 6 squared now. 6 times 6 is 36. So now you're solving an equation, x over x minus 9 is equal to 36. And you gotta reach back to those old algebra properties of how do I solve an equation where there's x's on both the top and bottom of the fraction? Good question. We could put the 36 over 1 and cross multiply. So it'd be 36 times x minus 9, and then it's going to be 1 times x. Yeah, and I think it kind of explains itself from there, right? Distributive property, 36x. I just happen to know that 36 times 9 is 144. I can subtract the x to this side, add the 144 to that side. Subtracting the x's gives me 35x. Adding the 144 to the other side is just 144. And then divide that by 35. And you get kind of a messy decimal answer. But what you can do to check your answer here, okay? To make sure everything is okay. 144 divided by 35 ends up being 4.114, okay? You now have to check your solutions. I should have done it with the first one. I really should have. I did it with the second one. Sorry, when I say first and second, I mean number 3 and number 4 in the notes. The first ones I've done on this video. 4.144. Plug it in. Does it create a negative for my first log? No. 4.114 is positive. Does it create a negative inside my second log? Oh, it sure does. 4 point something minus 9, 4.114 minus 9 equals a negative number. It's a negative number inside the log. Can't happen. Doesn't exist. Bad. This solution is bad. And it's the only solution that we had. Which means what? This is one sad little equation. There's no solution to number 5. So be on the lookout for extraneous solutions because they're hiding. You got to find them. All right, number 6. You know what? I want you guys to try number 6 on your own. Hit the pause button. Muster up some courage and go for it. All right, let's see how courageous you were. All right, I see base 10s. I am going to consolidate these two logs into one using this property right here. So log base 10 now of x times, oh boy, x plus 21 equals 2. All right, so here, keep some separation. So far, so good, right? Okay. Now we get rid of the log base 10 by exponentiating by 10 on both sides. I think I just made that word up. So then you cancel the log with the exponential there, and that gives me x squared plus 21x. All right, that's just the inside contents get multiplied together. You get x squared plus 21x. 10 squared is 100. And, oh, we got a quadratic equation. Maybe some factoring. Yes, you guys love that stuff. Maybe. Sometimes you love it. So, use either the quadratic formula or do some factoring. Just looking at this, 25 times 4 pops out at me, right? Because what's the difference between 25 and 4? 21. So if you had a positive 25 minus 4, that gives you 21 and multiplies to give you 100. So these two factors actually work out nicely to get that polynomial factored down. You can check me on my work there, but I'm pretty sure I'm right there. So x equals negative 25, right here, x equals 4. You ask yourself, do these solutions check out when I plug them back into the original? So looking at the negative 25 right away, it's like, no dice. You are negative right away. You're negative there too. You're doubly negative. That's an extraneous solution right there. 4? Well, 4 doesn't seem to pose a problem here, and 4 doesn't pose a problem there. 4 is okay. So x equals 4 is the only solution to this equation. All right. If you guys are experiencing a little bit of logarithmic fatigue, we've only got one more. Wow, looks like these are the only three properties we really need to know. So how about number 7? Oh, it looks like we got a mixture of the two. Looks like we got a mixture of addition between logs and a coefficient here. The question is, what needs to happen first? Do I need to have 2 clean logs before they can consolidate to give me 1 clean log, or can I just do it right away? You got to get that 2 out of there. This 2 needs to be rewritten as x squared. So this is log base 2 now of x squared plus log base 2 of x minus 1 equals log base 2. I should have put parentheses around these. Sorry. So that's our first step. We moved the 2 coefficient to a 2 exponent. Now these two come together. They consolidate to give us log base 2 of the contents x squared times multiplication now x minus 1. Other side, nothing changes. At which point we exponentiate by a base of 2. That gets rid of the log here, gets rid of the log there. Now you're left with x to the 3rd power minus 1x squared equals 12x. And just for kicks, I made another factorable polynomial. So you've got x, you can factor an x out of this. And because there's a clean x squared, we can use that same strategy of it's going to be x times something. All you got to do is figure out what numbers multiply to give you negative 12 and add up to give you negative 1. Negative 4 times positive 3. So the solutions to this equation right here are going to be x equals 0. X equals, you got to add 4 to both sides. X equals plus 4. And then you got to subtract 3 from both sides. It's x equals negative 3. So we got to ask ourselves, which of these solutions would yield kind of a garbage answer if we plugged it back into the original? So if you plug back into the original, here's a question. Can you take the log of a 0 value? Remember, this is what the graph looks like. You cannot. So if 0 is in there for the log, it's kind of like you're dealing with an asymptote type situation. And right there, log of 0. You know what? It would have come up to be a negative number here anyway, but just keep that in mind. You can't take the logarithm of a 0 number. Does 4 work? It gives me 48, gives me 3, gives me... Oh, sorry, I should go to the original, the very original. 4, 3, 48. No problems. Negative 3? No! 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 Okay, so x equals 4 is the only solution. All right, this video is pushing 21 minutes. I need to stop this thing and let you guys digest this. This is going to be kind of like a 2-day lesson, so if you feel a little overwhelmed by the amount of videos, well, I guess it's only 30 minutes. You shouldn't be overwhelmed. If you're overwhelmed, get back down to whelmed. All right, I need to stop talking here. Thanks for watching, guys.